So we turn now to the topic of using Taylor and Maclaurin series to find limits. This corresponds to section 10.10 in the textbook, but I just want to make it clear. 10.10 is on various types of applications, and we're really only doing this specific application from section 10.10. So anyway, this is the topic that we're doing. So if you think about how you would find a 0 over 0 limit, something you learned roughly three-quarters of the way through Calc 1. We used L'Hopital's rule. I mean, there were a couple of different ways that you could find 0 over 0 limits early in the course, but then eventually we learned that there was this thing called L'Hopital's rule. The problem with L'Hopital's rule is that you often have to apply it repeatedly. You apply it by taking the derivative of both the top and the bottom in a rational function, and sometimes you get just another 0 over 0 limit, and then you have to take another derivative. And sometimes these derivatives involve product rules and chain rules, and they just mushroom out of control in their complexity. So what we want to do is demonstrate a better way that makes use of a Taylor series for the functions that appear in the top and the bottom. So so let's do this problem. Let's evaluate the limit as x approaches 0 of e to the x cubed minus 1 over x squared sine of 2x. We can easily verify that this is a 0 over 0 limit. Since e to the 0 is just 1, we take 1 minus 1 on top, and that gives us 0, and on the bottom we have 0 times the sine of 0, which is still going to be 0. So the thing to recognize is that we can write out Maclaurin series for these expressions fairly easily. Recall that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. Make that n a little clearer. And that expands for the first couple of terms to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. So I can write that e to the x cubed is equal to the sum from n equals 0 to infinity of x cubed to the n over n factorial. In other words, just every place I see an x, just replace it with x cubed. So that becomes 1 plus x cubed plus x cubed squared is x to the 6th. That's still over 2 factorial. X cubed cubed is going to be x to the 9th over 3, and that's over 3 factorial, etc. So what I can do now is, since I'm trying to write the numerator as a series, the series is just going to be this series here minus 1, which means I'm just taking out that first term, and I can write e to the x cubed is equal to, I'll show you why this works in a minute. This is going to be the sum from n equals 1 to infinity of x cubed to the n over n factorial. Now, it's not the case that you can subtract 1 just by increasing the start of the series all the time. It just so happens that we know that the n equals 0 term is 1. So if instead I just started at the next term, it's like omitting the 1. That's not really the point. The point is that I really want to just look at the first couple of terms of the series, and this is going to be x cubed plus x to the 6th over 2 factorial plus x to the 9th over 3 factorial, etc. Sorry, I forgot that I meant to write this, e to the x cubed minus 1. That's what I'm trying to write here. Okay, so that's the series for e to the x cubed minus 1. Now, let's do x squared sine of 2x. First of all, we know that the series for sine x is the sum from n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Like all good Calc 2 students, we've all committed that one to memory, and that is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, dot dot dot. So we can write out the series for sine 2x just by replacing all the x's with 2x. So that's sine 2x is going to equal, I'm not even going to write it in this form, although I could. This is going to be 2x minus 2x cubed over 3 factorial plus 2x to the 5th over 5 factorial. I'm not going to keep writing because, as you're going to see, I'm not going to need terms all the way up to the 7th. It might just be a little easier if I expand these. So this is going to be 2x minus 2x cubed is going to be 8x cubed over 3 factorial, and then 2 to the 5th is 32 So that's 32x to the fifth over 5 factorial, and that's plus minus dot dot dot. So I now have a series for sine 2x. I want a series for x squared sine 2x, so I'm just going to multiply that series by x squared. So that means that x squared sine of 2x is going to equal 2x cubed minus, let's see, multiply the next term by x squared, so that's minus 8x to the fifth over 3 factorial, and then plus 32x to the seventh over 5 factorial, and we would keep going. So you're going to see we're not going to need any terms really beyond the first few of them. So let's focus on what I have here. I'm trying to find this limit, so I have e to the x cubed minus 1 over x squared sine 2x. Here are the series for those, or the beginning at least of the series for those numerator and denominator terms. So now I'm in a position where I can rewrite the limit in this form. I can write this as the limit as x approaches 0 of e to the x cubed minus 1 over x squared sine 2x is equal to the limit as x approaches 0 of x cubed minus x to the sixth over 2 factorial plus x to the ninth over 3 factorial plus dot dot dot, that should have been a plus here, over 2x cubed minus 8x to the fifth over 3 factorial plus 32x to the seventh over 5 factorial plus minus dot dot dot. Okay, so now what I have really are, I have these two series. Recall that I know many people are going to look at these and say, let's focus on the highest powers. Two answers to that. Number one, there is no highest power in either of these series because the powers of x keep ascending forever in both cases. Number two, this is not a limit as x approaches infinity, so it's not the highest powers we're concerned about. What we're concerned about really is getting something where we can get enough zeros to drop out. This is no longer a 0 over 0 limit. So what I'm going to do is I'm going to multiply this by 1 over x cubed over 1 over x cubed. So I'm going to divide in both the top and the bottom. Basically, I'm just multiplying the whole series by 1. And on the top and the bottom, I'm simply going to reduce every power of x by 3. So that comes out to the limit as x approaches 0 of 1 plus x cubed over 2 factorial plus x to the sixth over 3 factorial plus dot 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 over 2 minus x cubed over, or sorry, that's going to be x squared over 3 factorial. Oh, sorry, I'm not looking at the right one. 2 minus 8x squared over 3 factorial plus 32x to the fourth over 5 factorial, and then plus minus dot dot dot. The point is that if you look at this, what you can see is that since every term except the beginning ones have a power of x in them, all of these are just going to become zeros. These are all, when I substitute in 0, this becomes 0, this becomes 0, all of these terms become 0, and all I'm left with is 1/2. So this now just becomes, this just becomes 1/2, and that's actually the answer. So let's see if we can fit that whole thing on one page. So this is the answer, and we did it without applying L'Hopital's rule. Now, there's one thing to take note of. Focus on what I'm pointing to here. What you can see is that if you kept taking derivatives, since these are in fact the series that we were looking at, for the functions we were looking at, and we know that anytime we have a series for a function, it stands in for the function in every way, as long as we're within the interval of convergence, which is everywhere for these two functions. What you can see is that I'm not going to be able to eliminate the 0 over 0 limit without taking the derivative 3 times, because every time I take a derivative, I'm going to reduce the powers by 1, which means that the first time I do it, I'm going to have x squared. The second time I do it, I'm going to have x in both the numerator and denominator. It's only on the third try that I'm going to have x to the 0, giving me these constant terms. So now, think about what that would involve if I hadn't put the series in the first place. If I had simply tried to take these derivatives. Look at, they're fairly complicated. We've got a chain rule in the top. Once we do the chain rule once, we're going to end up with both a product rule and a chain rule at the same time. On the bottom, we already have both a product rule and a chain rule. In fact, I've written out what the first three derivatives are of these functions. For e to the x cubed, let's see, first, second, third, I'll write that. For e to the x cubed, the first three derivatives are 3x squared e to the x cubed, not too bad. The second derivative is 3e to the x cubed, 3x cubed plus 2. And the third derivative is 3e to the x cubed, 9x to the sixth, plus 18x cubed plus 2. So you can imagine that you would have, this is of course the simplified form. I just got this from a computer program. I didn't do it by hand, but what you can see is that you would have had to do quite a bit of computation even just to get to this. And you might say, well, don't simplify it, but you're going to have to plug values in, and you're going to have to verify that it's a 0 over 0 limit. So that in itself is fairly complicated if you were going to use L'Hopital's rule. Now let's put up x squared sine of 2x. This one, the first derivative is 2x sine 2x plus x cosine 2x. The second derivative is 1 minus 2x squared sine 2x plus 8x cosine of 2x. And the third derivative is negative 4 2x squared minus 3. I don't know why there are two sets of parentheses in there. I don't think that's right. Cosine 2x plus 6x sine 2x. So you can see that these derivatives are going to be fairly complicated to compute. In some cases, if you happen to know the series, I know I spent a lot of time finding these two series that you see in the blue boxes, but that was just kind of as a review. The fact is, finding this, once you know the trick, finding the series for e to the x cubed is not that difficult, and then subtracting 1 is also not that difficult for that. So getting to this point and this point is actually probably easier than taking the third derivative of some fairly complicated compound functions involving the product rule and the chain rule. So that's the reason to use this technique. It is an important application of Maclaurin series, which is one of the reasons that we demonstrate it. So anyway, that's it, and this is really most of what you need to get. Should be actually all you need really to get started on the section 10.10 assignment.